In this part 2 video, we're going to wrap up taking a look at the method for creating a position function for an object moving in 2 dimensions. So on the previous video, we set up the idea that if you had an object moving in 1 dimension, that you could track its position based upon its original velocity and any acceleration that it was experiencing using one single dimension kinematics formula. But if it's moving at an angle to a coordinate system, then any sort of acceleration in the x or the y direction is going to cause the object to change direction. So it's no longer a one-dimensional motion problem, it becomes 2 dimensions. As time goes by, the direction of the object's velocity will change. You got to account for that. So we broke down the initial velocity into its x and y components. We then made a kinematics equation for each of the dimensions. In this case, the x direction, we had an accelerated motion problem. And in the y direction, it was constant velocity. There was no acceleration in this y direction. Then we condensed all of that down into a single equation that told us the position r from the origin of the object based upon the time that goes by in the x direction, which we use the I unit vector to represent the x direction, and in the j unit vector direction, or the y direction. So we've got our position function, and we can plug in 0 seconds in here, and we would end up with 0 for the position because we said it started at the origin. We could put in 1 second, and we calculate what the position would be in the x direction and in the y direction, and then move the location of the object. So it's going to move along this direction pretty much in the beginning. Any small amounts of time, like 1/10 of a second, is going to get squared here, and it's going to be a very, very small impact on how far it's going. But as time gets bigger, the acceleration has a bigger impact. So let's go ahead and calculate out what the velocity of this object is as a factor of time, or as a function of time. And we can calculate the velocity as we would with any position function. We can say that the velocity is going to be the derivative of the position with respect to time. And in this case, the position is the r vector, not just an x vector, because there's an x and a y component. And so we can apply the time derivative to the whole vector all at once. We do not need to separate it out. We can have 7.1t minus t squared in the I direction, and the 7.1t in the j direction, and applied the derivative to all of it at the same time. So the I and the j unit vectors are really just multiplied onto this scalar quantity. They're multiplied on, they make it a vector. So because they're just multiplied on, the product rules for calculus apply, and taking the time derivative of this, that factor doesn't really matter. It's just a coefficient technically. So we'll take the time derivative of each part of this vector, and we'll get the velocity of our particle. Or in this case, I think it's a ball rolling on a tabletop. So we'd have 7.1 minus 2t in the I direction, plus 7.1 in the j direction. And the units for velocity are meters per second. Now, if you start taking a look at this, it's really just collapsing the 2 different dimensions of motion together. This is the original velocity, Vox, minus the acceleration multiplied by time. That's just the equation for the new velocity of an accelerating object as time goes by. So we're not doing anything new, really. We're just condensing 2 dimensions of motion together, so we don't have to have 2 separate lists of functions that we are taking care of. And then over here, that 7.1 is the original velocity in the y direction, and it's a constant. So the velocity in the y direction is always going to be the same in this particular problem. And if we go ahead and take a second derivative of the position function, we can get the acceleration as a vector is equal to the derivative of velocity with respect to time, and that would just be -2 in the I direction. which is the only acceleration that we had from the wind that we said was blowing on the ball as it's rolling across the table. So the kinematics formula still work. The relationships that we have used in previous units of study still work. It's a bunch of stuff together now. So sometimes that can be a little daunting, but it's one of those situations that we're not really making anything new or making something more difficult. It's just got an extra step in it. So it's the same stuff we've been doing before, just with an extra, dare I say, dimension added to it. We're just tracking the x and the y at the same time. Now, this is not the only way we're going to solve problems. When we do projectile motion, we're going to, for the most part, split the x and the y up completely and solve them separately, because sometimes we have an unknown that we need to find. But if we have a problem that gives us the position of an object based upon its x position and its y position, both as functions of time, we can find where it is at any moment in time. We can take the derivative and find the velocity at any moment in time. And we can also find the acceleration at any moment in time. Now, let's go ahead and take a look at an example problem together for this. So I have a sort of preview for projectile motion here, but the example is a cannonball is shot at 100 meters per second at an angle of 30 degrees above horizontal. Write a position vector equation for the ball, or the cannonball. So for the cannonball, we have its initial velocity. We know that, and we know it's at 30 degrees above horizontal. And if we want to write an equation for it, we're looking for something like r is equal to something I plus something j. That's what we want. We need to know what goes into the I and the j. So we'll start by establishing that the y direction is going to be the up and down, and the x direction is going to be the horizontal. And as we did before, the first thing that we did before we can put anything in here is we need to really figure out what our given values are. So original velocity is 100 meters per second at 30 degrees above the horizontal, as shown here. So if we create a triangle around that original velocity, we make it the hypotenuse. We make it the hypotenuse of a triangle with the angle theta there. We can figure out what the original velocity is in the x direction and the original velocity in the y direction, just using our trigonometry. Once we have that, we can go ahead and establish what the kinematics equation would be for the x direction and the y direction. And at that point, we can simplify things and we have a function for the position of the cannonball as time goes by. So let's go ahead and do that. For the initial velocities, VOY is going to be 100 times the sine of 30 degrees, and VOX, not VOY, will be 100 cosine 30 degrees. So we'll go ahead and calculate that out. Let's go ahead and make over here on the side, though, let's make a little list of the variables. This is going to be something we have to do for projectile motion problems. So for horizontal and for vertical, what do we know? Original position, final position, time, original velocity, final velocity, acceleration. Let's make that list for both, but I'm going to make it into y values for the vertical direction. Sorry for having a really ugly y there. And let's go ahead and put in the subscripts there. So horizontally, for most problems when we're dealing with free fall, we say that there's no air resistance. So that means there's not going to be any acceleration in the horizontal direction. There's nothing. It's freely moving. Let's assume this cannonball is very dense and it's not going to get moved around by the air too much. In the y direction, though, it should be negative 9.8. Got that acceleration due to gravity. For the other values, let's go ahead and let's just assume that when we start looking at it, that's our origin. And we'll say the original position 0, 0. We don't want to worry about anything else. Sorry, I got my highlighter thing over those numbers. The final positions, that's what we want to function for, right? So that's our question mark. Time times some variable that we'll have to plug in at some point if we want to calculate things, but we don't know what that is. But the original velocities we do have now. All right, so 100 cosine of 30 and 100 sine of 30. In the x direction, we'll have 86.6. And in the y direction, we have 50. Now the final velocity we don't know, and for most kinematics problems, you don't need to know all those things. So the time is just going to be our variable t. We can use the 1/2 at squared style equation in order to write a kinematics formula here. And we can make an x component equation using the stuff that's given and a y component using the stuff that's given here. So let's go ahead and move that down because I kind of ran out of space. And we'd have the position function r. Apologize, my little arrow there looked a little funky. Is going to be, if we write an equation in the form with the 1/2 at squared, due to the information that we're given here, we'd have original position 0 plus the original velocity in that direction, 86.6 multiplied by t, plus 1/2 at squared, but there's no acceleration, so don't have to put anything there. And we say that's in the I direction. And then we need to put in an equation for the y dimension, or the j direction. And again, we have 0 for our original position. We've got an original velocity of 50, and its original velocity is upward, so that's going to be positive. So 50t plus 1/2 our negative 9.8 acceleration multiplied by t squared. That's in j direction. All of that measured in meters. So we've got a position function that will tell us where the object is in 2 dimensions. It'll give us a point relative to its starting position in space, like a coordinate point, that will know where it is at any given moment in time. But let's go ahead and simplify this just a little bit. We got 86.6 t in the I direction plus 50t minus 4.9 t squared in the j direction. Sorry, my end bracket there looked a little bit like a big J. There we go. Now, again, that doesn't look like it's crazy easy to consider, but that is a function of time that gives us the position of the object. What's most important about this is that the horizontal, or the x direction, is not accelerating. There's no acceleration there. I guess I should put no, not. No acceleration. It's moving at a constant velocity. And in the y direction, there is an acceleration. Which makes sense because of gravity, but that means that every second that goes by, the projectile is going to go the same horizontal distance every second that it's in the air. In the vertical direction, though, it will, on its way up, begin to lose speed, eventually get to a highest point, and then start to speed up on the way down. Now, if you combine all those things together and you were to do a parametric plot for this, you would get a parabolic pathway, which is exactly what you would expect for something that gets launched into the air. And the mathematics is going to back that up. We'll go and stop that video here. I just wanted to go through the derivatives and also show a quick example of how you can set up a real-world problem using these vector positions.